Well, welcome again to another episode of Tech Command Investing, your go to podcast for insights into the cutting edge world of space, defense, and cybersecurity technologies, hosted by myself, Alain Gavin, a seasoned expert in deep tech investing and disruptive technology. Today, my guest is Jean-François Morizur, founder and CEO of Cailabs, one of the few startups in the field of laser comms. In this episode, we'll delve into the world of optical satellite communications and their strategic importance to both civilian and military applications. So let's just dive in. The vision. You started Cailabs back in 2013 by exploring what optical fibers could do. Fast forward to today, you're helping redefine communications between space and Earth. What kicked off this journey, and when did you realize it could transform space tech?
All right. Hello, everybody. Hello, Alan. I think it's a very good question because we started Labs based on a technology in a lab, and I was actually I did my PhD thesis, and we invented something originally for quantum optics, and we never actually went forward with that. It was there was a patent file, there was some good ideas. Um, And I left the physical field. I went to work at the Boston Consulting Group, and it was one of my PhD supervisor that called me back and said, "Oh, actually, there's an interest by a telecom company for that technology." And so I always had within me the idea of wanting to have an impact, and especially like the idea of having a technology that was lying around in a lab not being used didn't feel right to me. So I said, okay, I'll do that. So I started the company, and that was about fiber optics. It was about putting more data within a fiber. We got two world records with fiber capacity with Japanese telco KDDI, and then what happened was actually with a Japanese client, they pointed us towards the space application. It was 2018, I think. Um, and they did that because they said, okay, your tool that you're using to put more modes in a fiber is actually very useful, could be very useful to deal with turbulence when you've got lasers going through the atmosphere. So it tells us basically that you kind of don't have a set kind of path. I think the vision was to have a big impact with new technology in optics and photonics. But in reality, you've got a meandering path like a lot of deep tech.
Yeah, of course. It takes time to get to the right solution. Yeah.
Exactly.
So so following on from there, you've described Kylab's unique capability to mitigate atmospheric turbulence as a game changer. Can you break this down for our listeners? Why is this such a hard problem, and how have you solved it?
Of course. So when the laser goes through the atmosphere, so low, first off, let's take a step back. When the laser goes from one satellite to another, this is kind of a solved problem today. I'm not going to say it's an easy problem. I'm going to say it's a solved problem. It's already deployed in high volume, and there's a very big challenge around, having lasers working properly in space and having, pointing being very accurate from one satellite to the next. Now, when you go from satellite to the ground, it should be easier because the distances are smaller and you have a ground. So the ground is a little bit easier to deal with. You've got virtually unlimited power on the ground compared to what you've got on a satellite. But actually, it is complicated. It's actually more complicated because of this last layer, which is the atmosphere. The atmosphere is, 10 kilometers of air. And because, of course, a bit more than that, but basically, it's like what is impactful is those 10 kilometers of air. And so when the beam goes through the atmosphere, it is deformed. It's kind of change its shape,
Mm.
and this creates deep fades. This creates small cuts in the detection. You can see those cuts actually with your naked eye when you look at stars. I think everybody has been looking at stars. When you're a child or even later, and you see them twinkling.
Mhm.
Twinkle, twinkle, little star.
Yes, exactly.
Exactly. And so this twinkle is not the star itself. The star is a big ball of fire. Don't worry, it doesn't twinkle. Okay. It's
Right.
the interaction between the turbulence of the atmosphere and your eye, your detection apparatus. And so you've got the exact same problem when you reach the ground. with a laser. And those kind of twinkling, this kind of deep, we call it deep fades, can be a very big problem. If you detect it with your own eyes, it basically tells you that it's actually not such a fast event. It's actually something that happens for a long time, and this is a massive issue. And so what you need to do is compensate for the impact of the atmosphere. And so this has been a difficult challenge for a long time. This was an astronomy challenge before it was an optical communication challenge. And so people were using adaptive optics. Adaptive optics is a big surface that you push and pull to compensate the effect of the atmosphere, to compensate the effect on the phase of the beam. Um, it turns out that this is very good. This is a very good option for adaptive optics. So adaptive optics is a very good option for optical, for astronomy, but not such a good option for optical communication. It's relatively costly, which is completely acceptable when you're looking at, uh, an astronomy observatory in Chile, where you've
Yes.
got, tens of people working there and stuff. It's absolutely
It's
not a
very
problem.
niche. Yeah.
Exactly. It's a niche. You're going to do it a few times and stuff. So basically, getting high performance adaptive optic system is very costly, quite difficult to maintain. You need PhD students there and stuff. I worked with adaptive optic systems in my PhD. And so basically what it means is it's complicated to solve. It's a complicated to solve problem. So what we did is we sidestepped that. We decided to work with our ability to work with modes. So when we take the modes of light, so the different shapes that composes the turbulent laser beam, and we spread them out, and then we recombine two by two the different outputs that are on single mode fibers. This is kind of a relatively technical process. There are some papers published that we published. So anybody who wants to get more into details on this is like, I would point them to our website. Um, it's not trivial, but it's also quite easy to understand once you've got this kind of the basics of the
Right.
optics right.
So then moving maybe just a little bit deeper into that, because you have the traditional satellite communications rely on RF or radio,
Radio.
but with growing data demands, that's showing its limits. And you can see this illustrated in Figure 1 for audio listeners. You can download the figures at the link provided. For someone who's never heard of laser comms, how would you explain the difference in performance and potential of lasers versus RF?
Fundamentally, RF today, if you're looking at the commonly available RF bands, say Ka band, for example, it's a very well used band. You can get 3 gigabit per second on that band with if you're using the full band, if you've got the routes to use the full band. It gives you an order of magnitude. Of course, you can get a little bit better if you can like more exotic bands. Of course, you get less if you got X band, for example, it's only 300 megabit per second. So it depends, but basically the order of magnitude is there. On the other hand, optical can go very fast, and we already know that. I mean, your fiber to the home today, they can provide you with multiple gigabit per second, for anybody around. And in a data center or for long distance telecom, we're talking terabit per second on optical fibers. And it's possible to get to multiple hundreds of gigabit per second for laser comm from satellite to the ground and from satellite to satellite. Today, Starlink has been published that and said, okay, we're doing routinely 200 gigabit per second between satellites, for example, and they've got a path towards a terabit level kind of capacity between satellites. So this is the main difference in terms of pure capacity between RF and optical. We're talking 1 or 2 orders of magnitude in terms of capacity. So it's basically the cost per gigabit. It's how much data you can move around, and marginally. I think actually it is very similar cost. Sometimes laser can be actually cheaper than the RF antennas because they consume a little bit less power on the satellite and stuff like that. So assume it's basically same level of cost, and at the same time, 10 times, 100 times more capacity. So obviously, you're reducing the cost of data. Beyond that, laser is also something that is very difficult to intercept, very difficult to detect, very
Right.
difficult to jam. So it has another layer of benefit, especially on the strategic domain. And there is no frequency allocations because it's laser, it's directive, so you don't interfere. And that means you don't have to plan for frequency allocations. You don't have congestion on this. Today, X-band congestion for satellite communication is a nightmare. And I mean, there's been, recent reports on this. And I would point out that this is a big driver towards laser communication. And one of the big reasons laser communication was very fast um, adopted between satellites in space.
Hmm. And I mean, I think that's a very good point. I mean, also because I mean, it enables you to go much faster between satellites, but also to ground, and
Yeah.
because there's less regulation around it, you can innovate much faster. You don't have to check with the regulators every time you want to change something. I think that's a very important point. Yeah.
Yeah.
But let's have a look at now how it matters to investors. You've raised 46 million euros since inception, reaching Series C. Not bad for a deep tech startup in Europe, and it's absolutely fantastic that you've been able to achieve that. What convinced investors to back you, and what's next in your growth story?
That's what convinced investors to back us is probably something you need to ask them, not me. But I can infer from what they told us. I think there was an underlying technology that's very strong, and that's what they audited. I mean, every single round there was a deep audit on the tech. Um, this is something I like because it's basically it shows that they're serious. And I think in some domains today, speaking deep tech, you may have seen that some investors not being serious about um, the underlying tech can lead to issues down the line. So let's not name names. But yeah, and so basically, what happened is they backed us because of this underlying tech. They backed us because what they were seeing in the market. And I think there was, especially in the last round, there was this recognition that there's a hype around space and space investment, but they are within space, and for good reasons. There's a very high potential of what space can do and how space can be impactful,
Mm.
both on the sovereign level and on commercial level. At the same time, there's probably some part of space that is overhyped. And so some of our investors are saying they were basically looking at places that are not overhyped, that probably underhyped in space. So ground is one of those. Ground is something that, people don't think about when they think about space. They think about launches, they think about satellite, they think about all this fancy stuff that happens up there. And the ground part is kind of a little bit pedestrian. And so we actually had investors that said we are looking deliberately at the ground because we know the ground is necessary for the development of space, and it tends to be underhyped.
And so what's your next what's the next stage in your growth story? Where are you going from here?
We are basically in industrial deep tech today, so we are still investing a lot in going to next stages in terms of new products, getting the products to be ever more capacity, as you mentioned, 100 gig, 200 gig, more on that. We want to have ground stations that can be mobile, that can be transported. We want to be able to scale up our production facility in order to be able to meet the demands of the market. So we are investing in new facility. So that's kind of the operational growth of the company. And we're starting to get a good level of profitability on the industrial side. So we're still burning cash on the investment, but we're kind of getting basically a good picture of going forward what the business model is. So we're quite happy with that. There's maintenance, there's upgrades that we see are being something important. And related to investment, we're starting to see engagement from new type of investments. I mean, investors, sorry, a little bit less about venture, more about the growth stage investors. So it's interesting to see kind of the passing the candles from one to the next.
Right, from VC to private equity.
Yeah,
Yeah,
probably.
or more advanced growth investors.
Exactly. Yeah.
Yeah, just the point you mentioned there about mobile, making them mobile. Why is that so important? Maybe you can explain to listeners why it's
Of
important
course.
to make ground stations
So
mobile.
there's first off, I think the first layer is you need to make ground stations that work. Basically optical ground station in order to deliver good capability. In order to deliver capability, it needs to have a given size. And too small, basically, you'll be strongly impaired by turbulence. And too large, of course, it's a bit costly. And so basically, what happens then is that okay, how can I get the same amount of light collection and then put that on the truck? And why do you want a truck? You want a truck because in a conflict zone, you can deploy it. You can bring it closer to the front. You can bring it on tactical level, you're able to use it as a satellite communication tool that doesn't radiate, doesn't send radio around. And on a strategic communication tool, it's basically a way to communicate with satellites, say for deterrence. That is not something that just basically moves around. So it has additional benefits. So it is very important on sovereignty level to be able to move, but also in some use cases I've seen, having a mobile ground station is something quite useful to just send data back on the locations where it's difficult to get a data fiber. So
We've
we are working on that. But yeah, I mean, like it's all about there's no shortcuts. So you need to actually make sure that works and then put that on the track.
Yeah. Well, great. Um, Moving on maybe to the point about what signals should venture capitalists and limited partners be watching for that indicate that laser communications is crossing from niche to mainstream? What do you think will be the main sort of drivers and signals that you'd see in the market that is
I,
moving?
I think what we're seeing today is, I mean, clients buy ground stations from us in threes and fours and twos and so it's already something better than just the one for the demo. Um, the mainstream is when they refer to the programs where they're looking at 50, 100. And so the mainstream is going to be when we're going to move to that. It's probably going to be on contracts that are um, confidentials at the beginning, but those things are going to be sizable, so they're going to be relatively open, and it will be possible to see that. This is the moment when laser communication on the ground will be crossing from niche to mainstream. I would need to say that to clarify that laser communication in space has already crossed that. And I think that's something we need to keep in mind. Um, there's no architecture for constellations today that do not include laser communication between satellites. Um, Anybody who's got a constellation today that does communication has laser comm between satellites. Starlink already has thousands of those deployed. Kuiper has been explicit on the need for optical communication between satellites. Telesatellite Speed already also said that the same thing, and others. So basically, RE squared, sorry for the Europeans, same thing, laser communications, and the Chinese, obviously. So basically, I think we already moved from the niche to the mainstream in space. Basically, the next stage is to go from the niche to mainstream on the ground.
I just saw that Kuiper recently launched their first satellite at the end of April, so
Yeah.
maybe that is also already laser enabled.
Well, I would assume it is. In the architecture, that's what they're saying. And today, laser communication terminals, I'm not going to say there are like there's a lot of suppliers for laser communication terminals in space, and they're very good ones. Some of them are a lot of qualifications in space, and so I would say that it is very realistic that today the satellites that are being launched are all equipped with that.
Yeah, and we've also been hearing the signals from Miratlas, which is one of our portfolio companies that has been asked, about data for air turbulence and so on to be able to enable this optical communication. So it's definitely something. It's just the question is when will it move to mainstream? And I think you've answered that question. It's starting now already. Yeah.
Yeah, it does. I think we are a client from Euroclass in some cases, and they're providing good data on weather conditions, basically. What we find is that the locations of the ground stations are more driven by the availability of connectivity and optical fibers and logistics than on the precise weather or turbulence conditions. It's more like, okay, this is what we need to overcome there in order to make it relevant. And the people, this is kind of a fundamental thing for optical ground stations is that you don't want to put them in remote locations. It's not an astronomy stuff. It needs to be
Yeah.
deployed where you have a cheap connectivity. And
Yeah.
of course, if you go
And
on the
need
top of
for
a
the
mountain,
connectivity as well.
exactly.
Yeah.
Yeah, exactly. Of course. Yeah, yeah. You have to use on one side. And so it's, I mean, like, for example, one of the big use cases is data downlink. So bringing data back to the ground from, Earth observation satellites down to the ground. And this, I mean, basically means that on the ground, you need to have direct access to data center. And so if you've got 100 megabit per second or, a gigabit per second connectivity, um, and then, upgrading to 10 gigabit per second is going to cost you an arm and a leg because it's your remote location. that's going to be a big problem. So the good clients we've got, they basically are looking at this with the connectivity problem in mind, and that's very interesting.
So, and coming to that about, you're competing in a field dominated by legacy aerospace giants. What's your edge? How are you
Mm.
building defensibility around your technology, IP, and so on
Yeah.
to to build build out this new laser comms industry?
So on figure two, what you can see is the where Cailabs is positioned. So we focus on the ground. We don't do satellite to satellite connection, and we don't do terminals that go in space. This focus on the ground allows us to look at ground stations that are fixed, but are also mobile. But we are not a space company, and we don't put things in space. Basically, there are other companies that are really good doing that, and our job is to be compatible with all of them. So we consider them as our partners. So by concentrating investment, concentrating development, you're able to build an IP moat. You're able to file patents. You're able to be first in some developments. So you're able to win the contracts. And so you need to reinvest in development, reinvest in the industrialization to be able to win the next contract based on that. So fundamentally, um, when you look at the giants, they the giants, they also do a lot of things, and that's what we found is that aerospace giants are giants not because of laser comm. They're giants because they do rockets. They also do other radio. They do a lot of things. And so in order for them to say, I'm going to put a deliberate focus on laser communication, for example, and I'm going to invest, at tens or hundreds of millions in this in order to, unlock that technology and build a competitive advantage there. Um, they need a lot of people to greenlight that. They need a lot of people to assess this opportunity and to get validation and stuff like that. And if they didn't have those processes, if they didn't have that, they wouldn't be those aerospace giants. They need that. It's part of their DNA. It's part of their way of dealing with risk. And so this is where smaller companies have an edge, is we are able to assess risk and to assess investment, um, and probably concentrate technology and focus a bit more than the giants. What I keep telling people is that once the CFO General Dynamics realizes that this is a strategic field, we need to partner, we need to get acquired by a company like that. It's so important. It becomes important to them, then we become a good acquisition target. And until it's that point, then we are still the right people to push it forward. That's a good example. Of course, I took General Dynamics. It could be it could be Airbus. It could be like all of those aerospace giants.
Mhm.
So it's all about focus.
Yeah. Okay. And then maybe a last point on sovereigns. Why is laser communications becoming essential for modern militaries beyond just speed and bandwidth? How does it unlock next generation operations like real time battlefield coordination or autonomous swarming? And what other dual use cases, from disaster relief to telecoms to finance, make this a must have rather than just a nice to have?
Yeah, that's a very good question. Fundamentally, for militaries, it's not necessarily the high data rate, speed that is critical. It is the fact that its laser is not radio, and so
Boom.
it cannot be jammed, and it cannot be
Yes.
detected, intercepted. And when I say that, it doesn't seem very important, but today, radio antennas, and we've got data for that. Radio antennas, it's extremely easy to detect them, especially satellite radio antennas, because they need to radiate a lot in order to
A
reach,
large area. Yeah.
yes, and they radiate a lot in order to reach the satellite. And so what happens is they're relatively easy to detect, especially with good radar, and it's very easy to locate, so it's very easy to be shot. And so detection, not being detected, means you actually can be hidden. You can actually operate in zones where otherwise you would get a missile. So it's relevant for ships. It's relevant for people on the ground. It's relevant for command centers. And so I think for military, I think early this week there was a report from the UK DoD about the new strategy. And
Yeah.
they said for electronic warfare, they said the first shots of any war, including Ukraine, the first shot of any war happens in electronic warfare. It happened there. It happens like knowing where, detecting where your radio is or jamming, basically this is laser allows you to sidestep that. Laser is a solution to that. So when you've got, basically strategic reviews telling you this is where the first shots happen, this is why it's essential for modern militaries. Now it's not going to be only lasers. It's never going to be only lasers. It's always going to be multiple, communication tools. So radio is not going to get away. It's that you're going to use radio, you're going to use lasers, you're going to use a lot of things at the same time. This is already what people are using. In militaries, they've got in the US they call it PACE, primary, alternative, contingency, emergency, multiple communication channels. They've got different names in French, but basically what it means is you've got multiple options. And my guess is that it's going to be essential in the future that laser is going to be one of those, not all of them, but one of those. So lasers enable operations in an environment where electronic warfare is prevalent. And through that, you've got, but it enables battlefield coordination, as you mentioned. It can enable some crazy stuff to happen in a very data-rich environment. For basically dual use cases like disaster relief or telecoms. Telecom is an obvious one. Maybe you've got a Starlink antenna. Maybe you know somebody who has one. A Starlink antenna is you and me using maybe to watch Netflix or to do something else. It's a purely telecom use case, but it requires space, and you won't get an optical ground station in your garden. It's gonna be too big. But you have the gateway side of those big constellations will require optics. Today they're done in RF, but it is a bottleneck. When you look at 4 terabit satellites, that's what Starlink is projecting in the future. You cannot have 4 terabit satellites, going all direction and have 10 gigabit per second going to the ground. That doesn't fit. So you need optical also to the ground in those contexts. And so it's already public for some of the constellations, like Kuiper, that they're going with some optical to the ground, and I think we're going to see that more and more.
Mm-hmm. And to your point, there's figure 3 about the optical dispersion of RF versus laser, and audio listeners can download that as well. Moving on to a couple of questions on artificial intelligence. With AI, and especially generative AI, driving an explosion in data generation and consumption from edge devices to satellites, how is this influencing demand for laser comms? Are we reaching a point where RF infrastructure simply can't keep up with the bandwidth and latency demands of AI? So, yeah,
I,
maybe your thoughts on that. Yeah.
yeah, no, it's a good one. I think it's an interesting question because AI is both a way, for example, to deal with, to have compute in the satellites. And the good
Yes.
example, yeah. So you
Edge
have,
computing.
yeah,
Yeah,
exactly, edge
exactly. Yeah.
computing there. And so you could say, oh, I don't need to bring the data down because I already have a satellite that is computing things, and it doesn't need to download as much. What we're seeing, the paradox is that while people are using edge computing in the satellites, there's at the same time demand for bringing the same data down because you need to make sure that your AI doesn't do crazy stuff. So it's an interesting situation that AI as a tool to act fast in a satellite, I can totally go behind this use case. AI as a tool to reduce the amount of data going down, actually not so true. We've seen actually people say, actually, I still need more and more. And actually more like exactly to your point, the more people make their system smarter, the more you need to move data around. And so does that push to breaking point on RF? Maybe, maybe not. I would say it's more like the more we live in a data-rich environment, the more that pushes pressure on RF. Is it driven simply by AI? I would say it's more driven by anything that is data rich. So you've got, higher quality observation of Earth that will drive more data. Of course, it's going to enable AI So I would say, laser comm, it might be an AI enabler, but the interrelation is like not necessarily just driven by AI. If that can be the main thing.
Yeah, and expanding on that in
Mm.
defense and intelligence, AI systems are ingesting real-time data from growing number of sources, Earth observation satellites, drones on the ground, ground sensors. How critical is laser comms for enabling these systems to actually function as intended in fast-moving contested environments? And may want to point out Figure 4, which shows something about the expanding data transmission requirements, what we've touched in the question before. Your thoughts on that, yeah?
Yeah, so I think we're living in a data-rich environment. So you're getting more and more precise Earth observation data. You need to bring it back to command centers, but you also need to bring this big amount of data as close as possible to the people who are going to take the decisions. And usually the people that take the decisions can be on the front line. So you need to carry data everywhere. Is that exactly as you said, in contested environment? I think it's laser comm is critical when you want to carry a lot of data in contested environments. Probably, I mean, in an uncontested environment, I would say optical fiber is better.
Yeah.
In a way, if you're like between you and me, we've got Wi-Fi probably connecting to each other and optical fibers. And so in a kind of a normal day-to-day environment, optical fibers are there and they're everywhere. But when you get away from that kind of network that is kind of the infrastructure of the web, then yes, definitely you need laser comm as an alternative to radio. Because the moment it's jammed, the moment it makes it a target to missiles, so you need to shut it down. You cannot use your systems. What we're seeing is this explosion of data generating stuff. And in the past, it was difficult to make smart systems that would use all that data. Now with AI, you're able to build on a lot of information, a lot of data, and a way to process that in a way that we could not do in the past. So I think that we are creating more and more value, a lot of data. In the past, we would be probably more focused on saying, okay, this is exactly what I want to observe, and focusing on, a single piece of data. Now
Mm.
we're looking at more aggregate volumes.
Yes, and exactly to that point, I mean, maybe I'll run into the next section, which is about defense and
Yeah.
sovereign capabilities, which enables you then obviously to look further. And if you can look further, then it gives you more intel. You've worked with the French Ministry of Defense and are in talks with the US defense agencies. How is laser comms reshaping defense capabilities in real terms? And what changes on the battlefield?
Yeah, so of course, on these topics, there are some limits to what I'm going to be able to share,
Absolutely, I understand that,
obviously.
yeah.
But yeah, I mean, what is very public knowledge is that without laser comm between satellites, there are some use cases that you would not be able to deploy. Laser comm between satellites means it's very difficult to jam, and as a result, you're able to deploy capabilities such as deterrence that are a situation where you already kind of need to act in an environment that is very, very tough. Beyond those kind of very specific, I would say, strategic use cases, the local, basically tactical use case, the ability to bring optical data. One good example I keep giving is, radio silent communication for ships. A ship basically becomes a target when it uses radio close to places where people can detect it. And so sometimes they need to be in radio silence. At the same time, there's quite a lot of ships that also act as command centers. So there's a kind of a paradox situation where you've got a ship that acts as your command center. So basically, its main function is to communicate. And at the same time, they need to be in radio silence. So they cannot communicate anymore because of an external threat. So what I'm seeing there is, this kind of situation, it's extremely impactful to have laser comm. So we see them being, at the moment, being integrated in architecture, being discussed, being added to plans. And so I really like this moment because we are shaping the future of battlefields and of naval, both on the ground and at sea. And it's very interesting to see it evolving. Of course, there's some use cases that some people believe it's really smart, and then we realize, oh, actually, it's not, or the opposite. It's like, oh, actually, is there usefulness? And then it's like, oh, yes, there is. So we're discovering every day, and I clearly cannot say that we've gone to the end of that, and it's an obvious kind of a situation. There's going to be surprises in the future on this. I just love it.
Yeah, and then to your point about radio silence on ships, I was reading in a book about when the hypersonics come to pass, when the missiles become hypersonic, then your aircraft carrier, which is also a command center, can be blown out of the water in 30 seconds. Yeah, from anywhere in the world.
Yeah.
So the point about radio silence is very important. Yeah.
It can become, I agree, and then so basically it's all about being able to move and remain in radio silence. As long as people don't know where you are, you're good. The moment you start communicating, especially communicating with satellites, you're radiating a lot, and so that's why yeah,
Yes, exactly.
radar, yeah, exactly.
And compared to RF, lasers are harder to intercept, as I just mentioned, and jam. What real life military applications, ISR, intelligence, surveillance, reconnaissance, command networks, which you just talked about,
Yeah.
autonomous vehicles, do you see being radically transformed by this tech? So, what do you think is going to be the movers in the
I,
market to change everything because of laser comms?
I think I think it's more the opposite. Is that today electronic warfare is basically making it change. So a command network, autonomous vehicle, they are impacted drastically by electronic warfare. So basically, people are like, okay, what we assume we could do 5 years ago, 10 years ago, now we're seeing we can't. And it's pervasive capabilities. It's not like, oh, this very high end stuff that was restricted to just a few countries. Now it's like, I wouldn't say everybody has got that, but it's kind of prevalent. And so you've got this kind of looking at it and say, okay, we've got an issue. How do we evolve from that? What is the next step? And
Mm.
of course, there's like trying to find solutions with radio, trying to find solutions with you've seen maybe the Ukrainian drones with optical fibers behind those. That's a way to get away from radio. So laser comm, where does it work on this? Is it's basically providing solutions to those issue with electric warfares. Maybe it's going to be providing solutions to drone communication. Maybe it's going to be for command centers, for autonomous vehicle. It will depend on line of sight. It will depend on weather impact. It will depend on a lot of things. And there's some use cases where no, it's going to be completely stupid to look for optical comm, laser comm. For my good example is autonomous vehicle. For example, I would bet more on AI allowing you to out moving around, especially autonomous vehicle on the ground. You don't want laser comm to be your solution because the first tree is going to block it. So obviously, but on the other hand, for command networks, for ISR, definitely, then yes, laser comm is going to be a big driver because you need to transfer that information. It's not just act on it, but you need to be able to bring it back, and you need to be able to bring it back very often in a discrete way, making sure nobody intercepts that. So yeah, I mean, I think we're gonna see it there. Yeah, we're still, as I said, exploring that.
Yeah, I mean, talking about that, or your point about optical drones, and I've seen that the tethered optical
Yeah,
drones have had a lot of success on the
yeah.
battlefield. And the question is, obviously you have cloud cover, which is an issue as well, but if you had laser comms, then you'd in a good summer weather, then
Yeah, obviously, this is something we looked into. There's costs, complexities associated with that, scalability on some things, but it's not impossible. I would say it's more a question of when than a question of if.
So moving on to the next question, when you've got multiple nations operating laser downlinks from space in contested or overlapping regions,
Yeah.
South China Sea is one of them, or LEO corridors, for instance. How do we avoid interference or escalation? What kind of regulation or coordination is going to be necessary in the future?
And that's actually a very good question. It's tells you something, the difference between radio and lasers. Getting two laser beams to interfere is actually extremely difficult. From the satellite to the ground, the laser beam is 10 meters on the ground from LEO to ground, or 10 to 100 meters on the ground. In order to have an interference, you would need to have basically two satellites that are emitting in the same, roughly the same direction, but we're talking about two satellites closer to 100 meters to each other, and on the ground 100 meters to the two ground station. Then you would have some interference. If you've got two satellites that are closer to 100 meters, this is a nightmare scenario. This is called like a collision situation. It never happens, or if it happens, it's like a big failure.
One in a
Um,
million. Yeah.
yeah, exactly. So basically, it's newsworthy. So most of the time, like all the time, the satellites are much further apart, and this basically means that you don't have any interference. Same thing if you've got two ground stations that are close together. you typically own both. Like if you're the US military, it's very unlikely you're going to have a Chinese military with a ground station less than 100 meters from, the one you own. And as a result, basically you've got, and then so that's kind of the main difference between radio. Radio is kind of 40-kilometer situation. So a satellite to the ground, you're talking about, a radio size that's at, smallest you can do is about 40 kilometers. And so 40 kilometers is actually, you can have interception, you can have congestion, you can have issues there. Lasers, it's very, very difficult, almost impossible. And one thing we had a discussion about that is that we had people from the military, and they said, okay, well, if you've got somebody with a ground station that can intercept the beam, which is about 10 meters, 100 meters from your communication one, they said, okay, if they are 10 meters away or 100 meters away, they can throw a grenade. Like they need to intercept.
Yeah, you don't need
I
to
mean, I
intercept
already have a
your
problem.
laser com. Yeah.
Fundamentally, exactly. It's like, it's not like if they are within at the center of my base, they already went through everything. I'm already have a big problem. I'm probably not communicating anymore at this stage in the process. So the congestion on this is, it allows you to be far less stringent in terms of regulation coordination. And this has an impact on frequency plans. And we've seen that in, for example, when you've got militaries operating in foreign countries, they need to coordinate in terms of how they use frequencies so that they don't impair others and they don't impair the civilians there and stuff like that. And because a lot of satellite communication frequency, for example, there's the same ones as some 5G or stuff like that. And so it can be a nightmare to get the rights to use a frequency in a given location. Especially if you're in operation, like, you actually need to send people fast, something like that. It's complicated. Lasers just sidestep that. You can use it straight up. And so you're removing that issue, which can be a very, a big problem for some militaries. It can be a big problem for civilians too. I mean, if you want to be able to operate without without causing issues with the existing frequency plan of a country, I mean, basically, this is a very good tool.
Mhm. So maybe on the final question around this area of sovereignty and military, we're talking about more than just satellites and data speeds, as you mentioned. How do you see laser communications reshaping how nations project power, how industries run operations, and how civilians experience a hyperconnected digital world? How does that change with laser comms?
There's one thing that happens when you put everything together, when you've got extremely high data rates between satellites and extremely high data rates from the ground to satellites, is that at that point in time, you're able to have the equivalent of a telco in space. So you've got, AT&T, Orange. I don't know what kind of UK operators are there. Like, what's
British
the name? Yeah,
Telecom.
British Telecoms. Okay, so you've got British Telecom in space, and that has tremendous impact. Why? Because it makes access to the internet something that's not necessarily, it doesn't, it basically removes sovereignty to the access to the internet. So it's already a big question on, okay, if I'm accessing Starlink today, what about censorship? How can I make it, how can I, who is doing the policing of the internet access if I'm accessing a US, directly to a US company, for example?
Mm.
I mean, what would happen in some countries where they limit a lot internet access? Today, they're limiting, in this case, they're limiting Starlink antennas, or they're limiting all of that, um, because there's a RF component, so it's easy to police. What happens when you've got lasers and it's almost impossible to police? How do you do that?
Mm.
And so this has an impact on how citizens connect to an internet. It also has an impact on basically international policy. If I'm a country that able to bring in internet to another country, I can provide information. I'm able to broadcast information. When there's a coup, usually people, what they do is they take charge of the airport and the airwaves. That's what people do. The moment you've got the ability to bring internet in a country, independently from your telco operators, local ones that can be controlled, what happens there? Like, you've got a free internet access, or like an unregulated internet access around the world.
Totally.
Um,
Uh,
this is how nations, we know communication, not laser communication, like communication in general, has a massive impact on how nations operate, how the citizens live, and how we behave, how we make choices. And so this is a different channel and another way to provide access to information. So I think it's difficult to measure all the impacts, but they can be very significant. And in a way, how industries run operations today, I would say what we're seeing is optical communication becomes a backup, at least when your fiber is an issue. So you've got the resiliency that goes through, through space. I believe that for a quite very long time, it will not be economically efficient to, bypass. If you've got a fiber connectivity, it's going to be better to use fiber. Um, a fiber undersea cable is, we're talking 50 terabit, 100 terabits
Yeah,
of
much greater
yeah,
capacity, of
exactly.
course. Yeah, yeah,
So
yeah.
crazy capacity. I don't see, like, it's going to be a bit more costly, I think, to go through satellites. But at the same time, if there's been cut cable, or if you've got a complicated connectivity because you're in a remote location, you're going to be able to use satellite. And
Mm,
so you can imagine situations where, even for data centers, remote locations where you want a lot of processing, but connectivity is probably less important, maybe Bitcoin mining or stuff like that. Well, you want to put it somewhere where water cooling is going to be very, very cheap.
true,
So then
true.
you do that, and then you've got the your data bandwidth. Your data is going to be brought in by satellite. That's like a quite crazy option, but there's a lot of things I think that can be brought in through satellites with a pervasive, very high speed network.
Yeah, and I mean, you just sort of advertised my next podcast, which is about disinformation and how you.
Yes, definitely, I did that. I did not know it was the next one, but I completely agree. Yeah,
Yeah, so
and it's like, I think laser and being able to bring internet and having an open access to internet to a lot of people is something that can be brought through satellites, and in some cases can be negative. Definitely too much misinformation. At the same time, yeah, it's also like multiple sources can avoid having a single point of view on a topic.
we're just closing off.
Yes.
For those listeners who want to understand the future of this field, is there one book you'd recommend, or a series of books, something that captures the innovation and impact of optical or laser communications that would help people, understand, or a book that you would go to uh, to try and get
I
your.
I I would. It's an interesting question there because I've seen very good articles in papers, both scientific and like there's a very good one from The Economist, for example, a few months ago about the impact of lasercom and how that can, basically project country level kind of connectivity and stabilize and, remove coup and stuff like that. But in a way, I think I haven't seen many books written about it. I think it's relatively new topic. So there are very good technical books, amazing ones, but this is very relatively technical. So I would say it's a bit difficult to get in. What I would strongly recommend in people that want to get more into optical communication is there's a Reddit thread, for example, talking about lasercom. That's very, very interesting, and I would actually go there first, to be honest.
Yeah, we'll give those links to those two articles.
Exactly.
But great speaking, and yeah, I mean, thank you for being my guest today, and lots of success to Cailabs going forward in your exciting story.
Thank you. Thank you very much.
If you're an LP interested in learning about space tech, defense tech, and security, including cybersecurity investment opportunities, let's chat.